So hello everyone, in this video we'll look the forces on dislocation and force needed to bend a dislocation line. So when an external force of sufficient magnitude is applied to a crystal, the dislocation moves and produces a slip. And therefore force acting on dislocation line will tend to drive it forward. Now consider in the following figure, which is shown, the bold line shows the initial position of dislocation line, curved dislocation line, which is moving under the shear force tau in the direction of Workus vector B. Now consider an element ds which is to be displaced in the direction to the normal of ds by the amount of dl displacement. So now we have to find the force needed to have this displacement of dl. So first of all, area swept by this element will be, so area swept will be equal to ds into dl. Now the average displacement which is caused will be equal to, so average displacement which is caused will be equal to ds into dl upon capital A, which is the area of this plane, times b, because we will have the, at the end we will have the total slip of the magnitude of Workus vector. So for this intermediate region, we can say that ds upon dA times b will be the average displacement traveled. So now if I write the work done for this displacement, now that will be equal to tau into A times the average displacement which has been done. So now in order to find force, so force is nothing but dw by dl. But mind, this force is force per unit length, so we have to divide this dw by dl into the length of the element which we have taken as ds. So by rearranging the above terms from the above equation of dw, so we can get F equal to tau times b. So we obtained a result of force on the dislocation as tau times b, and this is force per unit length. Now let us move to the other part of this video in order to find the stress needed in order to avoid the bending of this dislocation. So once again, consider the following curved line as the dislocation line. So dislocation line possesses a line tension which minimizes its energy by shortening its length, and this line tensor is given by capital gamma, that is the surface tension force. So now let us have, as shown in the figure, let ds be the element, consider small element ds which subtend d theta angle at the center. So now in order to avoid the straightening of this dislocation, we have to balance the forces, that is force inwards equal to force outwards. So the force inwards is given by 2 capital gamma sine d theta by 2, and the outward force is the force which we have derived earlier, that is tau times b. But as this is force per unit length, so we have to multiply it with the total length of the element, that is ds. Now as sine theta is now in sine theta, the theta is very very small, so sine theta equal to theta, so we obtain tau d theta equal to tau b ds. Now if we integrate this equation, so theta goes from 0 to 2 pi, and ds goes to 0 to 2 pi r, which is the total length of the circumference. So we obtain capital gamma into 2 pi equal to tau b into 2 pi r. So 2 pi gets cancelled, and we get the value of tau as capital gamma by b upon r. So this capital gamma has a value which is equal to the energy of dislocation per unit length, so that is half gb square. So now substituting this in our earlier equation, which was given as tau equal to capital gamma upon b into r, we get it as gb upon 2r, and this is the force which is required to bend this dislocation.